Hello, we are going to focus now on what we call alternating series. So far, when we are looking at classifying a series, we have a list of tests that we can apply, and many of them apply only to series that have positive terms. We have two exceptions to that, the n-divergent test and the ratio test. Those we can apply to any kind of series. What we're going to study now applies exactly to series where the sign of the terms is alternating between positive and negative. So let me write how this series look like. So they are of the form -1 to the n plus 1. So that's the term, the factor that is going to make the sign change, times an. These are the terms of the sequence we're considering. And let's say summing from 1 to infinity. And the requirement over here is that an is greater than 0. So the terms are in principle positive, but then we multiply them by either 1 or -1, and then we make this series alternate. So this will be like when n is equal to 1, we get a1 minus a2 plus a3 minus a4 and so on. So positive odd terms and negative even terms. So this is what we call an alternating series. Alternating series. Okay, you may be wondering, what if we have something that actually alternates between positive and negative, but starts with a negative? So something like minus b1 plus a2 plus b2 minus b3 and so on. Well, that's not a problem because we can write this as minus the series that has the opposite sign, so it's going to be of the form -1 to the power of n plus 1 times negative bn and then n from 1 to infinity. So this part over here is an alternating series as well, and then we can classify it and decide if it converges or diverges, and the fact that we have to change the sign over here doesn't change the fact that it's either convergent or divergent. So that's not a problem. The important thing is that we change the sign from one term to the next. For this kind of series, we have what we call the alternating series test. Let me copy it over here. Basically, it tells us a way of deciding under some conditions whether an alternating series converges or not. So here it is. If we have an alternating series as I described it above, so a1 minus a2 plus a3 and so on, I make sure that this is really alternating by requiring that an has to be greater than 0. This series is going to converge if the following two conditions are satisfied. We need the limit of the an terms, so the terms without the sign, to be 0. And then we need to make sure that at least after some point, so that's what this n is doing, so at least for the values of n that are greater to some cutting point, capital N, the terms of the sequence an plus 1 has to be less or equal than an, so that the terms of the sequence are in absolute value getting smaller and smaller. So if we can check those two conditions, then we are sure that our alternating series is converging. Let's check that this works for a few examples. So we want to classify the following series. The first one is, I'm summing from 1 to infinity. I have a factor of -1 to the power of n plus 1. Then this is multiplying n over n squared plus 1. First of all, we need to check that this is really an alternating series. So let's notice that this part over here, this is an, and this is greater than 0. So this is really an alternating series, and we can try to check if the alternating series test works. So the first thing we need to check is what happens with the limit as n approaches infinity of n over n squared plus 1. Well, many ways of doing this limit. You can notice that this limit is going to be 0 because it's a limit of a quotient of two polynomials and the degree of the denominator is higher than the degree of the numerator. But if you need to write it down nicely, I'll take n squared as common factor in the denominator. So I'm going to be left with 1 plus 1 over n squared. And then that means that we can cancel one copy of n in the numerator and the denominator. And then we notice that this second factor in the denominator is approaching 1. And this is approaching infinity. And we just have 1 in the numerator, so this is approaching 0. So the first condition is verified. To verify the second condition, we need to compare the terms an plus 1 and an. And we need to make sure that as the index increases, the terms decrease. So we need to compare term with n plus 1 will be n plus 1 divided n plus 1 squared plus 1. And I want to check if this is less or equal than n over n squared plus 1. Again, I can think of a few ways of doing this. What I'm going to do is to look at the function fx, x over x squared plus 1. So this is a function that when I consider only the natural values, I get the terms of the sequence an. And I want to see that that function is actually decreasing. So it's decreasing, and I'm going to list after some point. That's what I need. And in order to do that, I'm going to check what is the derivative of this function. So I need to apply the quotient rule. Derivative of x, that's 1, so times x squared plus 1, minus x times the derivative of the denominator is 2x, divided by the denominator squared. So this is 1 minus x squared divided x squared plus 1, all of it squared. And then, well, the sign is given by the sign of the numerator, and this is less than 0 if x is greater than 1. Then what I'm saying is that the function f is decreasing for x greater than 1. And then what I can conclude is that fn plus 1 will be less or equal than fn for n greater than 1. So this, remember, this was an plus 1 and this was an. So the second condition is also verified. So we verified the first one, we verified the second one, and then with another color, we can conclude that this alternating series is convergent. So we classify our example. Let's see one more example. B is going to be this series summing negative 1 to the power of n times 2n over 3n minus 1. Okay, this is one of the cases that we have negative 1 to the power of n instead of n plus 1. That's okay. As I say, we can write this is going to be negative the sum of a series in the alternating form that we are used to. So with an n plus 1 over there, 2n over 3n minus 1. Okay, so this part over here, the 2n divided 3n minus 1, this is my an, which is actually greater than 0. So it is an alternating series as we know them. And then we need to check two things. We need to check the first condition, that the limit of the an is 0. And we would like to check as well the second condition, that the terms are decreasing. You may ask yourself if there is some strategy, if there is better to test first one condition or first the other. We're going to see here that actually it's a good idea to test the first one first, because then here, let's say we're doing limit as n approaches infinity to n over 3n minus 1. Yeah, so if we try to do this limit, we get 2 over 3. And that's not 0. So what we are concluding here is already that, well, okay, let's go slowly. First of all, we are concluding that the limit, if we take also in consideration the change of signs, is also going to be not 0. This is going to be oscillating between 2/3 and negative 2/3. So this limit is not 0. So just here, without doing anything else, we can apply the n-term divergence test. And then we can conclude that the original series diverges. So the series we started with, well, not exactly the one we started with, but it's the same, diverges. But if this one diverges, the one with the negative sign in front also diverges, so the original one diverges. So it's good to check the first condition, because if the first condition does not hold, then we can apply the n-term divergence test, and then we know that the series diverges and we don't have to do anything else. To finish this video, I'm going to scroll up a little bit and correct something wrong that I said earlier today. Well, I don't know if I said it, but I wrote it definitely wrong over here. Here, when I changed the sign, here I'm here, to make the alternating series look exactly the way we want them to look. When I changed the sign outside and then I change it also in the term, that's negative times negative. That will be positive. So I'll be back to the original one, and I don't need to change the sign of the terms bn. And I mean, actually, I wanted those terms bn to keep positive, so I'm not changing anything there. So it was just a negative sign that was extra over there and was not needed. And when we did apply it later on, here in the second example, we didn't have any extra negative sign, so nothing to correct there.